Good morning, everyone. Let's just give a few seconds here for everyone to join. Great, and we're coming to you live today from Pasadena in the San Gabriel Valley, just north of Los Angeles, one of the great centers of scientific innovation and technology of the United States. Just give a few more moments for people to join. This is our first CTrees webinar, and we're really excited to have you here today. My name is Daniel Melling. I'm the head of marketing for CTrees. And we're excited to bring you all here today to introduce Land Use Change Alerts, our first global forest monitoring system product. So for our agenda today, I'm just going to introduce our speakers and give you a little bit of background on CTrees. Our lead scientist for LUCA, Adugna Mullissa, will then give a presentation on LUCA. We'll hear a little bit from our CEO, Sassan Saatchi, about the context for LUCA and its applications and the other data products in CTrees' portfolio. And we'll also leave time for Q&A. So I wanted to just introduce you a little bit to CTrees. We are a nonprofit organization. We were founded last year, and we have a technical team and staff of about 30, with expertise in forest ecology, remote sensing, geospatial data, and carbon policy and markets. The idea for CTrees was really to bring science-based data for natural climate solutions. Our founders saw an important gap between the needs of carbon markets and the policy community and where the current advances in science and technology were located. Today, we are working towards a vision of building a digital MRV system to help make carbon markets and climate finance work. We are based here in California, and we benefit from global research and innovation partnerships, especially with our partners in France, Denmark, and Brazil. We are building a global MRV system. This is for measuring, reporting, and verifying carbon stocks, emissions, and removals globally. We have historical activity data as part of our platform. And really what we're bringing with the science and technology is the ability to measure at any scale, from smallholders to project developers, to countries and jurisdictions, and up to the global level on a consistent basis. We're also able to provide this data for any ecosystem on land, so not just forests, but also grasslands, savannas, coastal wetlands, mangroves, and so on. The point of the MRV system is to be automatic, accurate, and reliable, to bring greater certainty to markets and policy. So what does that mean for you as a user? We have several public data tools available now and coming soon. The first is our jurisdictional MRV tool, which is available on our website, which provides free data for every country and jurisdiction globally, including annual summary of carbon stocks, emissions, and removals, as well as a carbon map. This is being updated for next month, so please stay tuned. We launched our Land Use Change Alerts product just a month ago, and you'll be hearing very shortly from Dr. Adugna Mullissa about some of the features and applications. Coming soon is our pantropic degradation data, in which we'll be providing data across the Amazon, Central Africa, Southeast Asia on deforestation, degradation, and reforestation. Currently available by license is advanced MRV for jurisdictions and projects. This includes data to comply with Verra and ART-TREES standards for carbon credits. And we also provide carbon stocks, emissions, and removals historical deforestation, degradation, and regeneration data, and tree level data, which we're very excited to share more about later with Sassan. Before we get started with Adugna, a brief introduction to our two speakers. Adugna Mullissa is an expert in radar remote sensing and machine learning. He specializes in near real-time forest change monitoring. And at CTrees, he leads our synthetic aperture radar data product development and management. He comes to CTrees from the Netherlands, where he earned a PhD in radar remote sensing from the University of Twente, and he completed postdoctoral research posts at Twente and Wageningen universities. Dr. Sassan Saatchi is our co-founder and CEO. He is a research scientist, a senior research scientist at NASA Jet Propulsion Lab, Caltech, just up the street in Altadena. He is also an adjunct professor at the UCLA Institute in the Environment and Sustainability. And his research interests include the global carbon cycle, including the forest biomass and carbon dynamics, land use and land cover change, forest structure and regeneration, and the impact of climate change and variability on global forest function and resilience. Dr. Saatchi received his PhD from the George Washington University with a concentration in electrophysics and applied mathematics. We are really excited to have both Dr. Mullissa and Dr. Saatchi here today to share their insights with you. I just want to point out that we do have a Q&A feature, and so please put your questions in. I'll also be sharing some relevant links in the chat, including a feedback form for LUCA. So please, if you are using LUCA and have ideas for us on how we could improve it, you want to share what you're liking about the tool, if you have any other comments or feedback, send it to us. We will be listening, and we're looking forward to working with you to put this data into action. So without further ado, I will now pass it over to Adugna for our main presentation. Thank you.
Thank you, Daniel. LUCA is a near real-time global forest disturbance alert starting from 2018 until the present day. And this data is provided at an unprecedented detail at a 0.05 hectares minimum mapping unit. And this product is a culmination of cutting-edge scientific research combined with implementation and processing of massive amount of data in Google Earth Engine. And this data in the back end comes alive when we use our LUCA viewer app, as you can see on the screen, currently like zoomed over Central America. And with this tool, we can do visual analysis, we can do trend analysis, area analysis, and several other features. So I would like to use this opportunity to thank the Google Earth Engine team, which provided the resources and computation capability to process this massive amount of data, and also for Geo for doing the front end, to build this beautiful app. So LUCA is built to get a reliable, near real-time information on impact of land use activities on forest cover worldwide. So this means a lot of things for a variety of users. If a user is interested in making their supply chain deforestation free, as stipulated in the EUDR, that is the EU Deforestation Regulation, then LUCA can provide the valuable information. If the user is interested in stopping deforestation, fighting illegal deforestation, such as law enforcement agencies, LUCA can also have something for them. LUCA is also useful for participants in the voluntary carbon market, for policymakers, think tanks and academic researchers, media, and to be honest, for even concerned citizens that want to track, the state of deforestation and forest disturbances worldwide. So using radar surveillance to track land use changes have three particular benefits. The first is consistency, because it provides systematic observation of forest land use change, that is from forest to other land use. It has an added value of like having an accuracy because we map at a scale of disturbance using high spatial and temporal resolution of radar images. And we'll have the opportunity to have an all-time, all-land satellite coverage to produce alerts for forests across all biomes globally. So users may wonder, like, okay, what is the difference between using an optical image to provide these informations about forest change and using a radar image? So optical images are passive sensors, so acquired from nadir, but as you can see on the right, it provides a very nice image where you can clearly state the activity, the land use activity that's happening on the ground. But also for the radar, it's an active sensor. That means it transmits and receives its own electromagnetic pulse to form the image. So with that also, the mechanism is different, but you can see the activity happening on the ground. The difference happens when there is a cloud cover over like the scene of interest. With optical images, then you cannot see anything. But with the radar images, you use a longer wavelength, so you can penetrate through the clouds and still observe the activities happening on the ground. These have profound implications for near real-time forest monitoring, because in tropical regions, there is a pervasive cloud cover throughout most of the years. For example, in countries like Gabon, you may have like maybe 2 or 3 images, a handful, throughout the year, like cloud-free, ready for analysis and information extraction. So 3 images per year is not really sufficient to provide near real-time actionable information. So with radar, since we have timely acquisition of images that is not or rarely obstructed by weather, we can have a continuous and complete picture of activity, land use activities on the ground. Another important factor that I would like to mention over here is signal recovery, because in the tropics, because of moisture, after forest disturbance, the signal quickly recovers. After a few weeks, because of growth in the understory, the signal recovers, so it may not be as easy, to detect all the changes that's happening over there. So we need to do it like as quickly as possible. And radar provides a clear advantage in this regard. So we have seen like the benefit of radar images. So Sentinel-1 open data policy makes it a very attractive candidate for this task, because its spatial coverage covers almost the entire globe, and the temporal coverage is from 2014, officially it was then, but became available and temporally dense and ready like for analysis starting 2016. So that was our choice for building LUCA. We have a pixel size of 10 meter with a wavelength of 5.6 centimeter in C-band, and in dual polarization mode. That is, we have the VV and VH polarizations. So in one cycle, Sentinel-1 collects about 2.67 terabytes of data with a total of about 64,000 scenes. So this is like really massive data, spatially complete, but temporally dense. So this is a perfect candidate for us to build and fill the requirement that was discussed earlier. So for the methodology, first we defined forests as an area with a minimum of 10 to 15% tree cover and an average height of 5 meters. So basically this is a forest disturbance detection or forest change detection. Is a change detection problem. So we have to identify the forested area and detect when a land use change happens. And we define forest change as the complete or partial removal of trees in a pixel. So change is attributed in most cases to land use activities, especially in the tropics. And the forest change detection is applied on a global forest coverage in all biomes established by 2018. So the methodology follows 3 steps. First, we create statistical baseline features. Then we detect the forest change. Then finally, we validate. So for the first steps to create a statistical baseline features, like I said earlier, this is a change detection problem. So we need a baseline to compare any additional images that come so we can derive changes. So the first step, and the most important one, in my opinion, is creating the analysis-ready data, SAR data stack. So this is created by first removing outliers due to systematic issues or environmental occurrences. Then we remove the border noise. We apply a radiometric terrain correction to remove the effects of like topography. Then we apply a multi-temporal speckle filtering to remove or to reduce speckle. Then we do quality assurance. That is, we remove images with rain cells, and we also remove images with snow cover. This is particularly important in the high latitudes in boreal forests. So the statistical baseline features represent stable forests, and any change that happens after that is compared like with this baseline, to derive the changes. So for the forest for change detection, the probability of forest change is calculated for new incoming Sentinel-1 images in the monitoring period. So we established the baseline from 2016 until 2018, and starting the beginning of 2018, every image that comes in at every location is compared with the baseline to derive the probability. And the probability is driven using a machine learning algorithm. We reduce uncertainty by discarding false positives, and we apply post-processing to discard alerts, pixels that are less than 5 interconnected pixels. So what this means is we remove clutter or like noisy appearance in the alert. And after post-processing, the final alerts are provided at a 0.05 hectare minimum mapping unit. So to validate, we split the alert into 9 regions. As you can see in the image, in Europe, Africa, Asia, Central America, North America, Oceania, Southeast Asia, Eurasia, and South America. And we sample 450 stratified random samples from each region, and we applied area-adjusted accuracy for each region as suggested by the Olofsson's method. So we had an overall high global accuracy. We had an average commission error of 16%, an average omission error of 36%. In our opinion, since this is an alert, having an omission is better than commission error. We don't want to mislead anybody because it may involve law enforcement and other potential users. So we had a higher omission error. Okay. Next, I want to get into examples around the world with different drivers of deforestation and forest change. So the first one we see is selective logging in Central African Republic. As you can see, this selective logging is usually preceded by the construction of what's called logging roads. And this, in the image, as you can see, are linear features. And along the edges or the side of like this linear features, you see a lot of extraction of commercially viable trees. It may be for timber production or timber harvesting or for other reasons. So you can see the granularity of the detail of the data and the details that you can see in the captured image. So any potential users fighting, this illegal deforestation or for policy may find, I'm sure they'll find this kind of data to be very useful. The second one, also in the selective logging category, is the one in Suriname. I also find this to be fascinating because it looks somehow like a web, because the logging roads are so dense, and the selective logging around that is also really dense. So this is also from timber harvesting. And the third example I would like to share is from smallholder agriculture. This is around the city of Kisangani in the Democratic Republic of Congo. So as you can see, agriculture in this area is the main driver for deforestation and forest change. So definitely land use change is happening. And I found the pattern to be very fascinating, following the road, the river, and so forth. Another example of agriculture, but this time very large scale, I want to share is the one in Paraguay. As you can see, these are like really large scale deforestation that's happening. Each polygon is in the hundreds of hectares. So this supports a lot of agricultural activities. It may be for soya, it may be for animal, but you can see the extent of it clearly captured in LUCA. Next one is a mixture of small and large scale agriculture mixed in Sumatra. So the large scale agriculture is clearly from palm oil plantations, where the small scale agriculture may be from individual farming and so forth. So you can see the extent of it and how much it decimated the forest over there. So for law enforcement people, but also for policy people and carbon markets, this is a very valuable information because LUCA captures it like in great detail. Another one of the drivers I'd like to share is from mining. This is from the state of Pará in Brazil. You can see this is an alluvial mining for extracting gold and other like precious metals. And what's interesting is most of it may be illegal, falling on indigenous lands and so forth. So for law enforcement people, having this kind of information provided, updated every 2 weeks would be a valuable asset to enforce the law. Another one quite different from all the other one I would like to share is logging activity, but this time in Europe. So this is at the border in between Poland and Germany on the Poland side. So this is logging in a managed forest. So necessarily land use change may not happen because the area after logging also stays a forest, but you can see the activity clearly and it's quite striking, like the extent of it, but also the alignment and geometry of the whole thing. So I thought this was also interesting to share. Finally, in the example series, what I would like to share is the forest disturbance happening from wildfire, this time in California. This is not necessarily a land use change or something, but in North America, wildfire is one of the main drivers of forest disturbance. So LUCA captures this one really well. These are multi-year fire events in Northern California. So yeah, LUCA captures this one very well. So we can view the data using the LUCA app, but what's more is we can do area analysis from the weekly to monthly to yearly on a country level, on a state or province level, to the district level. If our area requirement does not fall on the 3 categories, we have the option to draw our custom ROI to do a trend and area analysis. I think this functionality makes LUCA very powerful to be suitable like for a variety of like users and applications. And what's more, to use these functionalities, you don't need any GIS training or knowledge. So it's quite user-friendly and ready to be applied to solve problems in the real world. If any of you is interested in knowing, and diving into the details of the methodology and techniques and so forth, for the pre-processing, you can check out like the middle reference for the methodology for the whole like near real-time alerting and so forth. You can check out like the first one was published, I believe, like 2 weeks ago in Remote Sensing of Environment. And for validation and accuracy assessment, you can check out the third reference. Back to you, Sassan.
Hi, everyone. I don't know if you can see me. Let me just share my slide. Okay. Thanks to Daniel and Adugna for the nice introduction and also on the methodology for LUCA. I want to get a little bit more into the implications of LUCA for both carbon market and policy, what is for in future happening for us to improve LUCA. We launched this first version of LUCA because we found that extremely timely and important to have this forest cover change alert system for both policy and also carbon market. There are a lot of activities going on both at the jurisdictional level and national level, and this year we have the global stock take, where a lot of countries will be reporting on their status of forest. So having a system of alert that can close to real time provide information on how forest cover change is occurring in different parts of the world is extremely important. However, having said that, since this is the first version, and like any first version product, it has its limitations and it also has a lot of room for improvement. So for the future of LUCA, we are thinking about several improvements, and this is going to happen in the next few months as we move forward. We try to actually update LUCA, different versions of LUCA, and it will be available on the Google Earth Engine for people to use it, download the information from it. So one is improving the baseline forest cover. As Adugna said, it's important to know exactly where forest and non-forest areas of the world are accurately, because if you want to detect the changes of the forest due to the land use, it's important to do that. Some of this baseline information is not really available from a lot of other sensors either. So I think we need to combine different type of information and also be mindful of the definition of the forest that is happening to kind of harmonize this information, have a baseline forest cover, and then detect changes afterward. We need to refine our detection in presence of a lot of environmental changes. As Adugna mentioned, it's possible that the change may not be due to the land use effect. We included fire specifically for North America because there is a lot of fire, especially wildfire, and also fire just occurring because this is the major source of the land use change or major source of forest disturbance in North America and impacting the emissions from different regions. We need to, having said that, we need to really include attributions to land use activities. Currently, we know that across the tropics, which LUCA was designed originally, most of the changes that we see on the forest is due to the land use activities and land use change. However, this needs attributions, meaning to define what is deforestation and what is degradations. And also when it comes to Northern Hemisphere specifically, we are mapping land use activities, but maybe not land use change, because most of the activities in the Northern Hemisphere is from the timber industries, and the timber industries do not change the land use. We need to reduce the omission errors. And this is important because for any alert system, you want to make sure that you don't have any false positives to detect areas erroneously as change. But the price for that is you sometimes have a lot of omission errors. That means you miss a lot of areas that have changed and you haven't picked up. Since it's an alert system, as long as for any regions you're picking up the changes, people can be informed easily, and it doesn't necessarily provide information in everything. So we need to actually reduce the omission errors to help the accuracy of what we are picking up. And the other thing is important is to improve the alert cadence to less than a week. And this can be only available when the next generation of the satellite data, radar satellite data, come on board to improve this. So going to the some of the immediate areas of improvement, which we are hoping to, early next year to attack these problems, is the inaccuracies in the forest baseline data. I mentioned that earlier. There's a lot of issues with the definitions, and sometimes there are areas near rivers which are not necessarily forest, or areas impacted by the topography, which is an important issue in the radar data sets that needs to be cleaned up and improved. One of the importance of areas of topographic complexity, such as submountain regions and mountain regions, is that with radar imagery, you have this shadow effect, and that blocks you from detecting areas the change is happening in the shadow. So Sentinel-1 had 2 satellites, and one of them failed a while ago. But the next year, we would have another satellite that allows you to always see the mountain areas from 2 sides. And that really improves significantly about areas around the mountains where changes are happening. And last but not least is to really look at the environmental factors, especially when there is snow and ice patches within the forest areas, especially in the northern hemisphere or on the top of the mountains, that can have a larger impacts or errors in our products. So one of the key things for the future is the launch of the new LASA satellite, which is called NISAR. It's the NASA ISRO, being the Indian Space Agency synthetic aperture radar. This provides you a much better frequency and wavelength, around 4 centimeter. It penetrates into the forest. It actually detects much better different variety of the forest structure. It has a resolution of 10 to 20 meter, depending what mode, and also provides polarizations that you can actually see the structure. The nice thing about the NISAR data is similar to Sentinel-1, it would provide data for every 12 days and every 6 days approximately on 2 different directions. So you can actually see the topography very well. All the data would be freely available on the cloud for people to use. All the algorithms for the data would be available for people to use and actually derive products. Currently, NISAR has 4 ecosystem level products. One is the biomes globally. One is the forest disturbance. The other one is monitoring all the wetlands globally, both in terms of forest and non-forest wetlands. And the last but not least is the agricultural areas. So together, this system and what we have already in LUCA can provide us a variety of the products that the alert system can expand to. So thinking about the alert system and LUCA, one of the immediate application of it, as Adugna said about monitoring, is to actually have a real-time signal of deforestation. And hopefully next year, when it becomes less than a week in terms of its cadence, it really helps for monitoring and enforcement. And that information, even though it's not exactly, it's only an alert system, but it can be used to provide an assessment of how much carbon emission is happening on a much finer time scale globally. So on monthly or weekly time scale, we would know approximately how much emission is coming from land use change. And that's an important thing because it helps us to have a much better estimates what's going on. Currently, most of the satellite data can provide estimates annually or sometimes with a lot of cloud cover in the tropics more than a year. So, and carbon emissions and removals becomes more accurate when you have a much better timely information. And then the data can be easily integrated in any national and subnational early warning system for the changes that is occurring for policy applications. I'm gonna cover few slides to just say how LUCA can be connected to other data systems, not only in our CTrees digital MRV, but other data products that can help to improve our assessments of what's going on globally on forest cover change and also nature-based solutions. One is having carbon map. CTrees has been developing carbon maps at 1 hectare resolution globally and also through time, which goes from 2000 to present currently. That gives you a lot of detailed information, as you see in the picture here, about the areas of deforestation and degradation across tropics and other ecosystems. And it also can be used directly for any kind of project level analysis or jurisdictional analysis, how forest carbon is changing and how intervention in terms of reducing emissions or any type of removal activities can help change the forest carbon. The next one is our activity data. We decided in CTrees to improve the activity data with attributions, and LUCA is one element of it, is to include both deforestation and degradation with attributions. Currently, forest cover change doesn't necessarily provide attributions, and we need these attributions for any kind of project level analysis, carbon credit, and policy. So we just published the paper, our team quantifying basically degradations from logging, roads, and fire in the tropics. With a very high accuracy, we used NICFI data from Planet, thanks to them providing data to the community. And then we're combining it with other conventional satellite data to create maps of deforestation and degradations and natural growth of the forest across the globe. And then last but not least, we need to quantify carbon outside the forest for two reasons. One, definition of the forest is actually extremely variable depending on where you are. There are large areas of landscapes that are tree covered, and this is an example in US, in California, you see, but also there are examples of it in Africa and other regions. They have large amount of carbon and can be used for nature-based solutions, for climate mitigations, and also helping small landowners who have trees or planted trees to improve their assets and also be participants in the climate change mitigations. So we have produced these data sets for the US. Our partner team in University of Copenhagen has produced this for Africa, and we are actually moving towards estimating tree, helping to actually improve the carbon emissions and removals globally. So last but not least, we were mentioning before that we have a jurisdictional MRV system, and that system platform is already been launched in 2022. We are updating it for 2023, which is going to be released before the COP, and you will basically get information on carbon stocks and emissions and removals for carbon credit at the jurisdictional level. We are focusing on improving these jurisdictional platform by including standards and methodologies such as the VERAS standards and R3s that are required with different groups to be developing carbon credits at the jurisdictional levels. And so what I look to suggest is to stay connected with us. We are providing, information at different levels in the next few months. And please send your comments and questions to us, and then also sign up for product updates and follow us on the LinkedIn and Twitter. Thank you so much, and we'll be ready to answer some of your questions.
Great. Thanks so much, Adugna and Sassan, for your presentations. We've been getting a ton of questions in the chat, and I've been trying to keep up and answer some of these by text, and others are still open. Just one kind of basic question. We are recording the webinar, and we will post it to the CTrees website. And we will also make the slides available to you after the event. So please stay tuned for that in the next couple of weeks. So I'm just going to summarize a couple of the questions that have come in. I think one is kind of a comparison to existing data products like RAD and GLAD. And I think the question is really like, what's new about LUCA? What are the the main new capabilities that weren't necessarily available before? So Adugna, maybe if you could address that question.
Yeah, thank you, Daniel. I don't think it's necessary like to get into like the comparison of like individual products, but I will highlight the capability of LUCA, because to my knowledge, it is the first global radar-based near real-time alerts. So this by itself says a lot of things, because as I explained in the presentation, the fact that it is a radar data set gives us a significant advantage over the optical one. And the temporal density that we get from Sentinel-1, even with the failure of Sentinel-1B, is still quite good. And we're not hindered that much by weather. And we go into like all forest biomes. So this by itself sets it on a class by itself. I don't know if Sassan has anything to add on top of that, but I would finish with that.
Just adding one point, I think there are a lot of alert systems going on, and we have been already contacted by WRI, who hosts actually several alert systems from optical and also RAD alert, which was originally developed from University of Wageningen. I think it's very important to try to bring this thing together. That's why we actually publicly released this data set. So it would be as part of our public good, and also combine it with other alert systems to improve this. So we are here to collaborate with other team members and other groups who are providing alerts to actually improve the alert globally.
Great, thank you both. We had a couple questions about the satellites that are underlying LUCA. One question was with Sentinel-1 and the difference between kind of the A and B. And another one is whether the biomass satellite that's launching next year has potential applications for forest monitoring like LUCA. I know Dr. Saatchi also described a little bit about the upcoming NISAR mission. So if you could maybe just give a recap of what satellites are currently being used for LUCA and what these new satellites coming online are going to mean for the product.
For LUCA, it's entirely Sentinel-1. So Sentinel-1B failed at the end of 2021. So starting 2022, there was no Sentinel-1B, it was only Sentinel-1A. So this affected somehow the orbits overlap and so forth. So the density of data that you can get like globally became lower. But from the beginning until the end, until Sentinel-1B failed, we used both Sentinel-1B and Sentinel-1A. After 2022, we used only Sentinel-1A. So yeah, it's only Sentinel-1.
I think for future, I mentioned NISAR, which is actually, it's a powerful system that's going to be launched in the spring of 2024. And that data would be freely available. And it's approximately gives you every 12 days, but both ascending and descending orbits, looking at the landscape in two different directions. So approximately every 6 days, you would have one image globally freely available. So combining that with Sentinel-1, we are hoping to bring the cadence of this alert to a week or less than a week. And in some areas of the world, especially Northern Hemisphere, it would definitely be less than a week combining the two data sets. In terms of biomass mission, which I am also part of the team from the beginning, the biomass sensor is developed mostly for detecting carbon stock, especially in the really high biomass areas in the globe, such as the tropical rainforest. And that's going to be launched. At least in the first phase of the biomass missions, the focus is carbon mapping. and it won't provide the frequent observations that you need for any alert system, but annually it would provide informations that can help us to also improve the forest, non-forest, or changes that are happening in the forest globally. So yes, any data comes from these radar satellites, we would incorporate in our analysis in future.
Great, thank you, Sassan. So we've had a ton of questions about access to the data, including whether it's possible to see it in the Google Earth Engine catalog, access an API, or upload shape files. Is there anything you would like to share about future access?
Would you like to? Okay, I'll say a few things. It's an open data, so ultimately, like, we plan on like making available the underlying data to users. But at the moment, we're working on a publication that accompanies the data. So unfortunately, that's not completely ready. And we need something like that, like to submit it to Earth Engine data catalog and so forth. So at the moment, it's only viewer, and the only data people can download is the charts generated like from the app. So yeah, that's it. But in the future, I'm sure we can work with different users on a case-to-case basis to provide the data as needed. So that's my thought on that. Maybe Sassan can expand.
Yeah, I mean, the question is, right now the app provides a lot of information that people need, especially building the statistics of changes that are happening for any region. When we update LUCA for providing attributions and making the land use change part of it more accurate, I think that would also help a lot for the information. The question is, would people have access to the imagery for download? I think we're working on it, and hopefully we will make the app possible for people to also download the images for that in future. This is part of our public good data product. So we hope that in any form the data can be used, we should be able to provide it.
Great, thank you both. We've had a number of questions, really interesting, about attribution and questions about the ability to differentiate between fire, what happens with regeneration, how does land use change differ from forest disturbance? Can you address a little bit what the alerts represent? And I know we've talked about adding more attribution features in next year, but if you could just touch on this kind of attribution question.
If I may, I think attribution is extremely important. So far, most of the data sets that we have globally has helped us to really monitor forest change for a lot of policy and market, but attribution is extremely important. Deforestation really means at least temporary forest is converted to either pasture or agriculture or settlement or change like this. So therefore, I think we need to do that. It's important. Remote sensing observations can provide that. And we are hoping by maybe combining and diversifying the input data sets, maybe radar alone or Sentinel-1 alone would not be able to do it. When NISAR comes in, it really helps with the attributions much better. And we combine that with the optical data sets, that it would improve it significantly. Remember, for attributions, most probably areas that has been changed, we don't need to update it so much. So the alert only is used to tell you immediately the change is happening. And then if we know the regions and how the changes happens in the regions, then we would be able to provide a better attribution. For example, when you look at the north or southeast of the US, where most of the change we are detecting are due to the timber industries clearing the forest, that has to be defined as forest remaining forest, not deforestation in form. So anyway, so I think attribution is extremely important. It's a challenging problem. A lot of people are working on it, and I think it would improve as we bring a lot of data sets together to make this happen.
Yeah, I think Sassan said it also. I'll leave it at that.
Great. So I have another good science question. We've had a few kind of specific areas, and one is, what is the accuracy in Africa, where some of the trees are dispersed and it's a slightly different forest structure. And another one is about slopes in the Andes. We had a similar question asking about terrain distortion. How are these accounted for in the LUCA alerts?
Okay, I'll take these technical questions. So accuracy over Africa, or in general over the pantropics, it's really high. So all the commission and omission error that we reported earlier, they are somehow like marked by commission errors that we observe in the northern latitudes, in boreal forests. That's where like we have like more commission. In Africa, commission error is below 10%. Have to like refer, like yeah, the person that asked that question can follow up, so we can provide like exact figures. But relatively in the tropics is much higher. To go to the second question of terrain, we use several protocols like to maintain the quality in the pre-processing after radiometric terrain correction. We masked out areas of layover, shadow, and we cut off like slopes exceeding a certain threshold that we set up. So we try to minimize the commission errors that we get due to topography. But this is a global data set, and everything is processed like in bulk. So controlling every location in the earth, it's very difficult. So that's why we indicated, you know, the area of improvement for future work. Yeah, Sassan, if you have anything to add to that.
Somebody mentioned Andes. Since I have worked in Andes a lot, and I still have a project across the Andean regions in Peru, I think there are a couple of things is important. First of all, these are areas that are extremely difficult to monitor with any system. Having said that, for areas where the slope is really steep and high, most of the forest cover change that happens in Andes, and we've quantified that in several papers, is due to the landslides. And landslides is the major source of disturbance around the Andean forest. Near the tree line on the top, and also at the bottom near the Amazon regions, there are land use activities happening, illegal mining is happening. LUCA can pick up those. And actually, if you look at the Peruvian side of LUCA, I checked this, it really captures a lot of land use change and disturbance in the lower altitudes and some near the tree lines on the top. But in the middle of Andes, where there are these, 70 or 80 degrees of slopes, it doesn't. And those areas are mostly impacted by landslides. And if there is any land use activities in those areas, currently we're not going to pick it up. And it's needs to be done in future. And this is something that most of the satellite data currently cannot pick it up very easily. Or if they pick it up, they cannot really attribute it to land use change.
Great, thank you, Sassan and Adugna. We've also had a question about the forest baseline, which is one of the features in the app viewer. Can you give a little more detail on where this comes from and whether it's going to be updated? Right now it's 2018, and there's been a few questions about just a bit more detail on that baseline feature. Thanks.
Okay, the forest baseline we synthesized from the 2000 Hansen forest cover dataset. Then from 2001 until 2018, we removed all the disturbances. So that's how we got the forest baseline, but this has its own limitations. We have indicated, like Sassan has indicated earlier. So this is one of the areas we'd be actively working on improving, because the alerts that you generate are strongly affected by the accuracy of the forest baseline data. And in my understanding, there are several groups, people, companies still working on further improving, this layer. So would also be doing that as well. Sassan, if you have something to add to that.
No, I think that you covered it. There are a couple of other questions that I see coming in about the accuracy, if we want to mention. One thing about Africa I just want to add was definition of the forest is extremely important in Africa. So a lot of sparse regions, both optical and radar data sets create confused data results or noisy results. We had to limit our basically detections to close to 15% of tree cover. And of course, for tree cover, we use the Landsat to set the mask that we are detecting this. But that mask can be improved in future. And then we can start picking up areas within the savanna woodlands where the forest or trees get impacted. It's not necessarily forest, but trees gets impacted. So I think stay tuned for future version. We can improve that. There was also another question, just want to bring it up about the use of methodologies that actually, like JNR and other methodologies, how this thing can work. We think that an alert system by itself, it can be used a lot for MRV within the methodologies, unless this alert becomes really validated to the level of accuracy the methodology wants in terms of land use, and also include attributions. In its current state, it would be only used for monitoring. Next generation of LUCA or similar products like LUCA would be directly then integrated in any methodology. And then along the same line, there was a question about NICFI data. For LUCA, we didn't use NICFI. NICFI, which is the planet data set provided by the help of the Norwegian funds development project, is currently available across the tropics, and we are using it with forest degradations and also mapping tree cover across the tropics. That data is extremely important for us. So I hope that the Norwegian development project would continue funding NICFI. It has been extremely useful. One of the advantages of NICFI is higher resolution and also data from hundreds of satellites, which allows you to see the land more often, where conventional satellites like Landsat and Sentinel-2, which are extremely well calibrated and nice data sets, but they don't provide that type of frequency of measurements at different time of the day. So I think we hope that NICFI would be used, and NICFI can also help with the attributions a lot. So we're hoping that we would use NICFI for the attributions of the land use change in future.
Right, we're now just coming to the top of the hour. So thank you again, everyone, for joining. We had more than 180 people at the webinar, and we're really just happy to hear your questions and feedback. Please continue to share feedback via the form. We love hearing from you. We are a science organization, so we're used to peer review. No matter what your questions and comments are, we really love hearing them. Just with the last remaining 30 seconds, Adugna and Sassan, if you have any closing thought, and then we will close the webinar.
No, I'll let Sassan go. Yeah.
No. Last question from Rachel Fletcher. Australia, we're going to improve our data sets for the Australian savannas. Having said that, I think there are tons of questions. We should record these questions and then respond to you later on. And so stay tuned and give us your feedbacks. Thanks so much.
Great. Thank you, everyone, for joining from Australia to Africa to wherever else you are in the world. We really appreciate you coming out, and we look forward to hearing from you again in the future. Please stay in touch, and we will see you again soon. Bye-bye.